Hey everyone! Today we're jumping into a really fantastic idea from vector calculus. It's called Green's theorem, and it shows this deep, almost magical connection between the edge of a shape and everything happening on the inside.
I mean, think about it. It sounds kind of impossible, right? How could you possibly know everything that's going on inside a park just by walking around its perimeter? Well, that's the central question we're going to answer.
The answer, as you might have guessed, is all wrapped up in this beautiful piece of math. Green's theorem is this amazing tool that connects the big picture on the outside to all the tiny details on the inside. So, let's break it down. All right, here's our game plan for this explainer. We'll start with the main idea, the boundary on the inside. Then we'll decode the actual formula. After that, we'll go over the rules of the game, check out its awesome superpowers, and finally, see where this all fits into the bigger picture. Okay, first things first. Let's get right to the heart of what this whole thing is about. It's basically a story about two totally different ways of measuring something that, and this is the cool part, end up telling you the exact same thing. So the main character in our story is this idea called circulation. Just imagine a vector field is like the current in a river. Circulation is just the total push and pull you'd feel from that current if you traveled all the way around in a closed loop. It's the net swirl you encounter on your trip.
And here's where it gets really interesting. There are two completely different ways you could measure that total swirl. The first way, let's call it the walk around the edge method. You just stick to the boundary and add up all the forces you feel along that path. The second way is the scan the inside method. Here, you'd look at every single point inside the region and measure the tiny, microscopic swirl right at that spot. Think of it like adding up millions of tiny little whirlpools.
So you've got these two methods, right? One from the outside, one from the inside, and here's the punchline, the big reveal from Green's theorem. It proves that both measurements give you the exact same number. The total swirl you feel on the boundary is perfectly equal to the sum of all those tiny swirls inside. It's incredible. The edge literally knows what's going on deep inside. Okay, so how do we write this amazing idea down using math? Let's dive into the formula. And hey, don't let the symbols scare you off. We're going to translate everything into plain English. All right, here it is. I know, it looks a little intense at first glance, but it's really just the story we've been talking about, but in math language. The P and Q are just the parts of our vector fields. You can think of P as how much it pushes you sideways, and Q as how much it pushes you up or down. Now let's really pull this apart. This table really lays it all out. That thing on the left, the line integral, that's our walk around the edge measurement. It's the big picture circulation around the boundary. And the thing on the right, the double integral, that's our scan the inside measurement. It's adding up all that tiny microscopic swirl, what mathematicians call curl, at every single point. Green's theorem is just that powerful little equal sign in the middle, connecting those two worlds. Okay, so as with any powerful tool, there are a few rules you have to follow. You can't just use it anywhere, anytime. So let's go over the rules of the game for Green's theorem. Yeah, think of it like a quick checklist before you start. Number one, your path has to be closed. It has to start and end at the same spot, a full loop. Two, it has to be simple, which means it can't cross over itself. No figure eights. Three, you gotta go counterclockwise. This is important. It keeps the region you're measuring on your left. And finally, the field itself has to be well-behaved. No weird breaks or jumps. If you got all that, you're good to go. All right, we know the idea, we know the rules. Now for the fun part. What can this thing do? This isn't just some abstract mathematical idea. It has some serious superpowers that make it a total game changer in places like physics and engineering. Superpower number one is just being an amazing shortcut. Let's say you have a really nasty, complicated path, and you need to calculate a line integral along it. It could be a total nightmare. But wait, Green's theorem gives you an out. You can just swap that hard line integral for a double integral over the nice, simple area inside. And a lot of the time, that's way, way easier to solve. Okay, this next one is just wild. It seriously feels like a magic trick. If you pick just the right vector field, Green's theorem lets you calculate the area of any shape, no matter how weird and wiggly it is, just by doing an integral around its edge. Let that sink in. You can find out how much space is inside just by walking the perimeter. It's awesome. And this is one of the formulas that just pops right out of the theorem. It looks so simple, right? It's just saying the area of some region is equal to this specific line integral around the outside. It's such an elegant and powerful way to handle what could otherwise be a really messy area calculation. And get this, This isn't just theoretical fluff. This principle was actually used to build a real physical device. It's called a planimeter. You just trace the outline of a shape on a map with it, and it tells you the area. It's literally Green's theorem made out of metal and gears. And this same core idea is a huge deal in things like fluid dynamics, for figuring out how liquids flow, and in electromagnetism. Okay, for our last section, let's pull the camera back. Because as cool and powerful as Green's theorem is, it's really just one piece of a much, much bigger puzzle. It's a peek at a truly universal idea in mathematics. You can think of Green's theorem as the flatland version of a bigger 3D law called Stokes' theorem. And there's another flavor of Green's theorem too, the flux form, which is all about how much stuff is flowing out of a region. And guess what? That idea also has a big brother in 3D called the divergence theorem. So you see, this isn't some isolated trick, it's a fundamental pattern that shows up again and again. So if there's one thing to take away from all this, it's this. In the world of vector fields, the edge of something and the inside of something aren't really separate. They are tied together in this really deep, fundamental way. What happens on the boundary tells you the story of what's happening inside, and vice versa. Which leaves us with a really cool question to chew on, doesn't it? We've seen how a one-dimensional line is connected to a two-dimensional area, so what happens when we go up another dimension? How does a 2D surface, like the skin of a balloon, tell you what's happening in the 3D space inside? Well, that's a story for another time.